This video is going to discuss specific heat capacity, which is covered in pages 519 to 521 of your textbook. Specific heat capacity is really an attempt to answer the question, how do substances absorb heat? It turns out that you can have a heat source that supplies heat to two different substances, and they're going to absorb heat in different ways. Specific heat capacity is an attempt to describe the ways that those different substances absorb heat. So in order to help measure heat, we have this concept of something called specific heat. And the definition's up here. It's the heat energy required to increase the temperature of 1 gram of a substance by 1 degree Celsius, which seems to make absolutely no sense. So let's look at an example and see if we can make sense of this definition. So if I am heating a pan on the stove, so we want to consider three things here. We want to consider the pan, we want to consider the water, and we want to consider this little plastic handle. Okay? So you apply the same heat to the pan. The pan is going to probably heat the fastest. Okay? It's going to absorb a lot of heat and its temperature is going to rise. The water is going to heat the next fastest. It's going to get hot. It's probably going to start to boil. But the water is going to get hot after the metal. But even after the water's boiling, you can still touch this plastic part with your hand because it does not heat very quickly. Okay? So specific heat is the heat energy required. Okay, so that's how long I have to put this on the burner to increase the temperature of 1 gram of a substance by 1 degree Celsius. So think about this. Which of these is going to have the highest specific heat? The metal, the water, or the plastic? You should answer the plastic because you have to put in a lot more energy in to heat the plastic the same amount. The metal has the lowest specific heat because the metal is going to get very hot with just a little bit of time on the stove. So specific heat is a characteristic property of a substance. Specific heat measures the amount of energy it takes to raise the temperature of something. So as you can see, water has a pretty high specific heat, followed by ethanol. Ice is underneath. And as you'll see, these metals here all have pretty low specific heats. And then you have granite and concrete in the middle here. But metals have low specific heats because it is easy to heat them. It's easy to change their temperature. You don't have to put in a lot of energy to change their temperature. These other substances, water, basically, they have very high specific heats because it takes a lot more energy to raise their temperature. So that's why you go to the pool in the summer, right? Because even though the temperature outside is very is very hot, the water will still be cool because it takes a lot of energy to increase water's temperature. So water will stay cool a lot longer than, say, the concrete pavement that you've got to walk on to get to the pool. After a hot day, that concrete pavement hurts. You got to put on your sandals. But you get in the water is still pretty cool. So you have the same sun heating both the water and the concrete, but the water has a higher specific heat, so it's going to stay cool longer. The concrete is going to raise its temperature with the same amount of heat from the sun. So better conductors are going to have lower specific heats. So we actually have an equation that we can use to relate the temperature change to the amount of heat that's transferred. And that equation is that Q equals mc delta T, or Q equals mcat. So m is the mass of the substance, C is the specific heat, delta T is the amount the temperature changes, and Q is the amount of heat that you have to apply. And we measure heat in joules or kilojoules. So if you measure a change in temperature, you can figure out the amount of heat, the amount of energy it takes to change the temperature by multiplying the mass times the specific heat. So here are a couple of examples. So first off, if you have a piece of metal with a mass of 4.68 grams and it absorbs 256 joules of heat when the temperature increases by 182 degrees Celsius, and they want to know what is the specific heat of the metal. So we have our equation, Q equals mc delta T, Q equals mcat. You can rearrange the variables such that C is equal to Q divided by m delta T. And then we plug in our numbers. So the amount of energy that we apply is 256 joules. The mass is 4.68 grams. And the change in temperature, because the temperature is increasing by 182 degrees Celsius, that's just 182 degrees Celsius. So the specific heat is 256 joules divided by 4.68 grams divided by 182 degrees Celsius. So we should get 0.301 joule per gram per degree Celsius. This next question. So you have a boulder, a granite boulder. The specific heat of the granite boulder is higher than the specific heat of the metal in the previous problem. That's 0.803 joules per gram per degree Celsius. The mass of the boulder is 2.00 times 10 to the third grams, and its temperature is changing from 10 degrees Celsius to 29 degrees Celsius. So again, we have Q equals mc delta T. And we plug in our numbers. 2.00 times 10 to the third grams is just 2,000 grams, but only these three are significant. We have 0.803 joules per gram per degree Celsius. We subtract the temperatures here, right, because we want the change in temperature. So the change in temperature is the temperature that we end with minus the temperature we start with, and that is equal to 3.05 times 10 to the fourth joules. So I hope this made sense. Really, the specific heat is kind of like the molar absorptivity when we did Beer's law. It relates how much energy you have to put in to raise the temperature. So hope you took good notes. We're going to do a few more practice problems in class. But we're going to add a new layer of complication. So just make sure you understand this level. And I will see you tomorrow. Have a great night.